Okay, deal. Perfect. Cool. So for those that are here, the person I guess to my left on my screen is Sam. She's wonderful and amazing and has the most amazing reputation, and she deserves it. She's gonna help us out at Brightwater. Our plan, as mentioned, is Monday to go to Brightwater. So Sam's gonna help us a bit, just talk about some clothing tips, given that we had Snowmageddon kind of hit us um, on Sunday evening and Monday. So, Sam, if you don't mind, go ahead and give us some tips. Cool. Yep. Yeah. That's how asking questions online usually goes, Sam. Yeah, yeah. What are your rules with masks when we get out to Brightwater? Mhm. Huds Yeah, Hudson asked, "Is there going to be a worksheet that we walk on?" I'm assuming he meant work on at Brightwater. You did, yeah. Yeah. Cool. Yeah, yeah, it is. Yeah. Um, Taryn asked, "If you don't have snow pants, are jeans warm enough?" So just to make sure I heard you correctly, if you have leggings underneath your jeans is the best option or some other non-cotton pant. Oh, she left. That was what she said. I do believe. So Taryn, if you have leggings or something to put under your jeans, that would be probably the best course of action. Hi, Sam. It's super cut out. So you said leggings underneath jeans, is that correct? Okay, sweet. Does anyone else have any other questions for the lovely Sam? You prefer to go by Sam, right? Oh, she froze. Oh, awkward. Okay, cool. Okay. Good luck, Sam. Have fun shoveling. I'll probably email you at some point and just some other questions, but we'll go from there. Thank you so much for being here. Okay. See you, Sam. I think she said have a good day, but I don't know. Okay. Um, so things I need you folks to accomplish. In order for us to go to Brightwater, I did post a Brightwater permission slip on your Google Classroom. That must be filled out and returned to me prior to us leaving. So, what that requires is a parent or guardian to fill that out. Once you have done so, then I will put a check mark beside your name. You're good to come to Brightwater and work on that. If you are unable to come to Brightwater for whatever reason, I will have other tasks for you to work on. So the schedule is that, and I'll say this in class as well, that 12:30 is when we need to be on the bus leaving towards Brightwater. We'll return at 2:15, and once we're back, I'll just let you leave. We'll call that a day for the classroom. So I don't know how long it'll take to get to and from. Obviously, I've been in touch with Sam quite a bit just with the weather and things to expect. So regarding the pants situation, I just wanted to make a comment from my personal life. So currently, if you were to look at my garage at my house, it is empty. My car is not located there. It is about 50 minutes, a 50-minute walk away from where my house is. I got kind of stranded on the Sunday evening. So I don't have my car. Um, Me and a buddy of mine, my roommate actually, we walked back home and both of us were wearing joggers. Highly do not recommend wearing joggers. The bottom elastic of the pant actually caught all of the snow and ice and ended up getting frozen. And my roommate actually ended up getting a bit of frostbite on his ankles. So covering up and stuff, that's important. We'll talk about that again for sure more in class. I'm going to just flip over to my iPad here, which I believe is the host right now. And I'm going to throw up the notes for today's class. Share content screen, start broadcast. I am also recording this right now, and I will post it to YouTube at a later time here. Um, and then if your friends or whatever else miss, or you want just like a rehash of everything we went through in class, that'll be there available to you. So one note here, we're gonna only go over just a little bit of stuff today. Um, this is mostly review, but it's also sort of an introduction to what Sam and you folks will be going on an adventure with um, come come Monday next week. So introduction to ecosystems. Again, some of this will be a review for you. Some of it we've briefly touched on in class already. But yeah, so some major connections, biosphere systems within this biosphere, how energy flows through the system, how nutrients cycle through the system, feedback loops, stability of living systems, productivity of living systems. Those are some of the things we will talk about. And so this picture, super blurry, I see on your Zoom. So let me see if I can make that a little bit clearer here. Basically, we break living land or living part of our universe into three components: the hydrosphere, atmosphere, and lithosphere. The biosphere, or if we think about the translation, that would be the life circle, is everything. It includes everything. So you can see that the biocircle here is this. The pen is not working. Wonderful. The pen is this circle around kind of the main area here. Curious why this isn't working. Oh well. Okay. And so if we keep scrolling down, the biosphere. I don't have a notes package for you, so that's why I'm just making this video. And also, it would be unreasonable for me to ask you to print out all of these pages. So that's why we're just doing it this way. The biosphere is the portion of Earth where living biotic organisms interact with one another in their non living abiotic environment. So if the biosphere is everything, that means that living organisms on Earth are interacting everywhere. And what's interesting is that all of those parts are interconnected. There's that word again that we've seen many, many times. That all of the biosphere, all the parts of the biosphere are interconnected. Air, water, soil, and organisms create a system of energy flow and the cycling of matter. This is just kind of explaining in words what that previous picture we saw was, that the atmosphere is that layer of gases around the lithosphere contains the Earth's crust and upper mantle, so the ground that we walk upon, and then hydrosphere, obviously being the water. In terms of the atmosphere that exists above us, the troposphere consists of about 75 to 80% of the Earth's air mass, and that's what's closest to the surface. Now, interestingly, and I think Gavin made a comment about this in class, it's mostly composed of nitrogen gas. The stuff that we actually breathe in and absorb is the oxygen gas, and then there's a bunch of miscellaneous gases, so water vapor, carbon dioxide, argon, methane, etc. The balance of those numbers is very important, and we will talk about in this class when we discuss climate change why those numbers need to be where they are, and why they need to exist at that level there. The stratosphere is from 17 to 48 kilometers above the Earth's surface. It's mostly the same composition, but less water vapor and more ozone. So that's getting towards that ozone layer that protects us from UV rays from the sun. There's a bunch of different kinds of UV rays that come from the sun. All of them have the potential to be dangerous to us, and that ozone layer blocks out the most harmful ones. So here's a bit of a better picture. troposphere, stratosphere, and then mesosphere is actually above the stratosphere itself, and it's above the ozone layer as well. So you can see on this image just where different things would exist. Mount Everest being at the absolute peak of the troposphere, and then where planes would fly over, going over top of that. Lithosphere, as we talked about, that was the Earth's surface and the Earth's core. It's where the solid rocky shell of the planet exists. And the lithosphere is actually broken up into things called tectonic plates. And those tectonic plates have the potential to actually shift and move. One of the hypotheses of how the Earth existed is, I'm sure you've heard about Pangea, which is where all of the continents were at one point together. And then, due to shifting tectonic plates, they broke apart. That is one potential hypothesis of uh, of how we got the different continents. There's different religious thoughts as well. Um, from an indigenous perspective, from a Muslim perspective, there's different hypotheses, or I guess religious beliefs, of how those continents started to exist. But what the crust actually contains is our non-renewable fossil fuels and minerals, and then also renewable soil chemicals. Those would be things like nutrients that are put there by plants. Hydrosphere, as we mentioned, is the water layer, the liquid water found at both the surface and also underground as well. There is water that exists underneath our soil as well. And so I imagine that when you do some of the soil sampling at Brightwater, just because of how icy it was recently, I would imagine that you'll see some of that ice in the actual soil layers as well. There is also water vapor in our atmosphere when it condenses or when it precipitates. That's where the water vapor eventually ends up. So that's kind of the three main ideas here, talking about the lithosphere, the hydrosphere, and the atmosphere. Those are the main spheres that we need to be concerned with. And then, as previously mentioned, the biosphere contains all of those living things. Thanks, Kirsten. So, what we get into then is something called open and closed natural systems. So, we've haven't really touched too much on these. They should have been something you talked about briefly, very, very briefly in Science 10. So a closed system is a system that receives both inputs and produces outputs of energy, but not matter. So what's notable here is that the amount of matter that we have on our planet is finite. You cannot create nor can you destroy matter. You can just change the way it exists. So, for example, if let's say I boil water, it's not that I'm destroying the water, I'm changing the state, or I'm changing the form of what that water exists in. Let's say that I chemically decompose something with an acid. I'm not destroying that thing, I'm just changing it into something else, some other type of matter. And that matter cycles amongst the various parts of the system. It doesn't ever leave or enter the system. So the idea with a closed system is that there is nothing coming or going from the outside of it. It would be like if you, as a human being, existed, you did not require to breathe, you did not require to eat, and you did not require to defecate. You were just a blob. Nothing comes in or out of you. You just exist. That would be a closed system. But as we know, human beings are open systems. They require both input and they have output of energy. You probably have eaten something already today. You've input energy from the outside into you. And if you had coffee this morning, coffee is a diuretic. Odds are you also went to the bathroom this morning, meaning you had an output of energy. So that's what an open system is versus a closed system. An open has things coming and going inside of it. A closed system just exists and that's it. There's nothing coming or going, there's no materials leaving or coming into it. Earth's natural systems. So, as far as the ecosystems exist, we spent a lot of time on that in grade 10. Ecosystems have both flows and storages, transfers and transformations. So, things are changing in location, they're changing in state, they're changing in their physical nature, their chemical nature. And what that allows is that allows energy to flow through those ecosystems, and it also allows nutrients to cycle through those ecosystems as well. There's millions and millions of moving parts in just a small patch of grass where energy is being transferred, exposed. Something's coming, eating the grass, something's defecating on the grass. It's now growing. There's water coming in. There's always a constant cycle. And that's why nature, I think, is amazing. When we look at energy, you would have spent some time looking at a chart that looked like the one on your screen now, where you have producers, primary consumers, secondary consumers, tertiary, and quaternary. In essence, what that means is one consumer, two consumer, three consumer, four consumer. And we would have talked about that as either a food web or a food chain, that there's a dominant species and then there is something that produces it. And so when we look at the first law of thermodynamics, this was that law I was talking about earlier, where energy cannot be created or destroyed, but it can change from one form to another form. And so organisms, what they might do is they might absorb energy from its surroundings, or they might give up energy to its surroundings. The most important process on this entire planet is photosynthesis. If we did not have photosynthesis, no life and no relevant life would really exist. Human life would be impossible without photosynthesis. And what photosynthesis is what photosynthesis is it turns radiant or sun energy into a chemical energy, and that energy is expressed by glucose or sugar molecules actually being produced. In order to make molecules, you need energy to do so. And that's sort of what photosynthesis does for us. It creates two valuable resources, which would be sugar and oxygen, as you can see by this equation at the bottom here. The second law of thermodynamics is that when you convert energy from or whatever you're converting, if it's energy from one form to another, some of that energy must be degraded into heat. So if you were to get up from your phone or your computer right now, sprint across your room and sprint back, odds are your body temperature would rise slightly. So it's not that you can just take all the food you've eaten and translate it strictly into physical energy that allows you to run faster. You also must produce heat. If you've ever cooked or if you've ever done baking or anything like that, you'll know that there's almost always some heat that gets released into the environment. Now, we're not losing that energy, it's just being transformed into a different form. And this second part is important here. No process that requires an energy conversion is ever 100% efficient because much of the energy is dispersed as heat. So if we want to take, let's say we want to make a solar powered car, that for us will never be able to be 100% efficient because we will always lose some of that energy from the sun as just heat, heating up the earth. In the same way, if we want to convert wind energy into an actual energy for a car or for power, in that process, in the long string of processes that gets us to that point, we will burn some of that as heat. Energy flow wise, the sun provides solar radiant energy, and then plants, algae, and cyanobacteria are able to capture that energy through photosynthesis. So it's not just plants, it's also bacteria and algae that do photosynthesis for us. And then, as we talked about, that energy gets converted into glucose or into sugars. Living things, what they then do is they utilize 90% of that chemical energy, so from the glucose, for either mechanical energy or it gets released as heat, as we've talked about. And then 10% of that organisms, ooh, yikes, chemical energy can be passed along to the next level of a food chain. And so this is sort of what you would have seen in grade 10, looking at the food chain, that at the very lowest, this would be called an energy flow chart or an energy pyramid. At the bottom there, the primary producers, 9,000 kilocalories. So a lot more energy at the very bottom. In the primary consumers, 900, secondary, 90, and then tertiary at the very top, the bare, 9 kilocalories. So you can see that as you get higher up in the food chain, there's less and less and less energy to be produced. Or because we're transferring it through so many different levels, we said that you only get about 10% of it. Well, if you're only getting 10%, then that explains why we go from 9,000 to 900 to 90 to 9. Each step up is another 10% taken off. The video in Planet Ocean, one of the things we watched, we talked about how much energy is required to like feed a human being. Another thing that was talked about is like how much water is required to feed a cow, for example. We'll watch a Mark Rober video on that. But if we look at this here, to feed a bear or to feed, get the energy required for a bear, you need 100,000 kilocalories of trees, shrubs, ferns, grasses, and flowers. So obviously, those should be and must be the most abundant things that we have on our planet. The issue is that that's not necessarily true, and we're making changes so that it's not. There's two different types of trophs. There's autotrophs, which they capture and convert energy into a chemical form for their own use. They don't require to eat anything. They're sort of self feeders, is the word I use there. Those would be things like plants, for example. And then heterotrophs, which is us, is that we are unable to convert energy into usable form and we must consume others. You can think about it as like driving an automatic car. You do not have to shift. There's no energy required to shift. It just car does it for you. And then heterotrophs, you can think of that as like a manual or a stick shift where you actually have to physically change the gears of your vehicle in order to keep moving forward. And then there's obviously a couple different terms there. Herbivores, you only eat plants. Omnivores, plants and animals, which is most of us. Carnivores, animals. Scavengers, they feed on dead organisms. So that would be crows, slugs. Detrivores, detritivores, sorry, breaks down the remains of organisms. So this is an example of an Indonesian rainforest. On Thursday, I have a super wild story to tell you about a guy from Yorkton who went. He's a pastor in Yorkton. He went down to marry a couple people who were living in the Amazon rainforest, and so I'll tell you some stories about their experiences there. We call the different levels of feeding, we call them trophic levels or trophs. And so primary producers, those are always at the bottom, are the autotrophs that convert their own energy into sugars. From there, we have primary consumers, usually heterotrophs, secondary consumers, heterotrophs, tertiary consumers, also heterotrophs. So the only ones that are the autotrophs would be the grass, trees, shrubs, plants that we sort of talked about already. And we sort of talked about this briefly already when we were looking at this diagram. We said that a kilocalorie was a unit of energy. And we said that when we want to build that pyramid of energy, we'll look at how much is available at each level. So the amount of energy available to the next level is about only 10%, which is why we went from 9,000 to 900 to 90 to 9 in that particular pyramid. Some of the issues within trophic pyramids that affect the energy flow. So you might not always get exactly 10%. In theory, that's the number that you'll be able to achieve. In actuality, that's not the whole truth. So things that can happen would be invasive species. The word alien is used, not indigenous, so not original to this environment, where the introduction of that species causes economic, environmental harm, or it can even be harm to human health. And so what happens is we have sort of the survival of the fittest happening. And the idea is either this invasive species or the OG, the original species, will become the dominant ones and will either drive one to the point of extinction or cause the number of other species um, to take over. And so Kai just made a sweet comment, which is that, yeah, honeybees are an invasive species to North America. Um, One that I mean we're running out of here. But yeah, that's a great comment, Kai. Thanks for adding that in for sure. So what can happen with these invasive species is they can shift or they can replace trophic levels in their new environment. They can change the balance that's been previously established. And obviously that's a very dangerous thing. Anytime you mess with nature and you mess with the very delicate balance of nature, that's a dangerous thing. Bioaccumulation, again, if we translate that to English, that would be life accumulation. When a toxic substance or pollutant from the environment becomes way more concentrated than it should be within a specific trophic level of the food chain. So, as an individual organism or group of organisms in the same environment at the same trophic level are repeatedly exposed to that, it can sometimes cause it can cause death or lead to death. And obviously, if enough get impacted by that, that can lead to extinction as well. So this is kind of just a diagram of what bioaccumulation is like. So showing those contaminant levels over and over and over time. Now, biomagnification is a slight difference in that. It's when a pollutant or toxin becomes increasingly concentrated, and then that gets passed from one trophic level to the next. So, if we imagine some of these smaller bacteria here, if we imagine them getting filled with a contaminant as it moves up the food chain, that contaminant will spread and grow because each level up the trophic level, they require more and more food. So bacteria, I mean, they're getting most of their food from the sun. Whatever's eating those bacteria, well, it requires more bacteria because they're only getting about 10% of the energy from them. So that's kind of what biomagnification and bioaccumulation are like. Does anyone have any questions so far? Hudson's asking a great question that I'll get to. This is a great pause. So Hudson asked the question of when is the exam going to be due? Currently, what I have told some other people is just, let's just say on Thursday, hand that in at that time. So you have, I guess, an extra couple of days because it was supposed to be due Tuesday. Let's say Thursday, get that handed in. I'll try to mark it. I doubt I'll have it marked by the Friday, but by the Monday, then we'll be able to start getting those portfolios kind of reviewed, or Tuesday because we're at Brightwater. So yeah, let's say Thursday for that, and I'll actually make an announcement on the class here. Um, I'll do that right at the end of the lesson here. That's a good question, Hudson. Laurier was asking a question too that I thought was awesome, which was, should we be just copying and pasting from our notes or putting things into our own words? What I responded to her was just, hey, I like things when they're in your own words because for me, what that allows me as your teacher to see is what level of understanding do you have, or how are you understanding it? I do not ever profess or claim to be the best teacher in the world. And in fact, I was telling Kaylee the other day that sometimes I just stink as a teacher. I don't explain things well, and it's something that I'm learning and trying to fix. Obviously, I'm only in my second year of teaching, but if you are able to understand something in one way, maybe I need to teach to that. And so I like seeing those things when you're able to, do them in your own words. Malachi, I will just have a quick chat with you after about that question. All right. Nutrient cycles. You would have heard the term biogeochemical cycles. It's a long term, but basically it just means the cycling of living nutrients or things that are required for life to exist. You would have seen this. This is just simply the water cycle. You would have seen this one last year as the carbon cycle. You would have seen this as the nitrogen cycle. You would have seen this as the phosphate cycle. And so you would have eventually seen maybe not this exact diagram here, but just the cycle of nutrients and how it actually exists. It's always in a circle that we eventually want the nutrients that were taken out of something to return to that place. And the key from all of these cycles was that without the water cycle, nothing can happen. The water cycle is the absolute mandatory cycle that must be in place. So this first statement says, as nutrients are finite, so there's a limited number of resources, they must be cycled. We'll talk about these diagrams probably a bit more in class, but for now, there's not much point in me delving too much into them. Photosynthesis and respiration. I spent way too much time in my degree looking at respiration and photosynthesis as well. Photosynthesis, very simply, is converting radiant or sun energy into a chemical energy, and that's when carbon dioxide and water are used to make oxygen. That's the stuff that we breathe in. And then, fortunately for us, it's a cycle of we breathe out carbon dioxide, which is exactly what the plants need for that process to happen. If you look at these two down here, they're the exact opposite reactions, with the exception of the ATP. CO2 and H2O go to C6H12O6 plus O2. And then the reverse of that when we're breathing is C6H12O6 plus O2 goes to carbon dioxide and water. Okay. I posted these earlier today. We have finished the first unit. Obviously, you guys received that quote unquote exam. We've finished the first unit. And so, what I would like you folks to do is take two or three of these questions and answer these. This will be included in your next unit of content. So, we are actually moving forward into the hydrology or into the water ecosystems unit. And so we're going to start looking at these questions more in depth, but I want kind of an intro reflection from you. So I'd like you to take three of these questions and just include those in a portfolio. When we return on Thursday, I'll give you a divider so that you can separate the different sections of that portfolio. Kai, the due date for everyone with any portfolio, the due date there aren't really, but they are when we go and look at your portfolio. So when I am looking at your portfolio and trying to say, hey, this is Kai's grade for this portfolio, um, that's sort of the due date. So we'll probably start looking at portfolios and having conversations individually on the Tuesday of next week. And at that point, whatever's in your portfolio, that's what I'm looking at. If you want to supply more evidence later, that's for you to come and have that discussion with me and show me so I can kind of adjust your grade as I see fit. But as terms of a due date, my recommendation is always get as much as you can done in class. If it's a take home assignment that I would like back in my hands to actually put a mark on, then yes, I will assign you a due date and I will say, "Hey, I would like this at this time." But if it's a reflection, I don't necessarily need you to um you don't have to finish it. But at the same time you're missing out on some potential easy free marks for yourself as part of that portfolio inclusion. Malachi, I guess I can answer your question now. In terms of the abstract, for yourself, omit that part because you were not present in class at that time that we had the discussion. And so what you and I will do then is have, as we're reviewing your portfolio, I'll describe to you kind of what an abstract is, and then we'll go from there and we'll progress from that point. You bet. Other questions, comments, concerns?